Good morning. All right, so a couple of things. I noticed the typo on our Moodle page, but I think we've already talked about what 7.4 is, but I just wanted to highlight a couple of things. We're heading into our last 2 weeks of school. It's crazy. It's crazy, right? Let's see here, share saved photos. And I wanted to, oh yeah, let me just remember it's at power calculations for a difference of means. We're not doing it, that's why I don't remember what it's called. So here, one typo is this should be power calculations, which we're not going to do together. Okay, you can read it if you're interested, but it's not going to be tested, and so we're going to skip it. Not covered. / not tested. Okay. So 7.4, we're skipping it. And so today we're going to talk about the difference of two means. Now, I know I made you work a little bit more than 50 minutes, but I know you guys are watching in time and a half, so felt like it was okay. And it was kind of a longer explanation than probably you needed, but on Friday or whenever you watched it, you watched the paired data video. Okay, and so I'll do a quick recap, but if you haven't watched that, it doesn't really hinge on, or what we're doing today doesn't really hinge on it. I will refer to it, but you can kind of learn them separately and it's fine. Okay, so I also posted these two assignments. Now the assignment 11, I did it on purpose. It's I think it's like 4 questions or something really tiny, and that's so that you can get your grades up, right? It's nice to have high assignment grades, and so I do that on purpose sometimes, as I throw a little cheapie in there. Okay, and then you'll have the 1 sample mean assignment, and then after today I'll post the 2 sample means, which includes paired data as well as the difference of 2 means, which we're doing today. Okay, and I cannot remember when these were due, so let me go check. On Thursday, the 7th, and the reason for that is because you've got your quiz on Friday. Uh-oh, there's a lot of information here. All right, so again, so quiz 4, same as the other quizzes, right? You'll have the entire weekend. It'll be available for your Friday class if you wanted to use that time, but you don't have to, right? So again, it's going to be open over the weekend. Oops. Open over the weekend again. And it's only on chapter 7. So only these means questions, which means that these are due on Thursday, April 7th. Oops. Okay. There will be an assignment for the 2 sample means, like I said. So that one is a little bit of work. And then for the ANOVAs, I just want to do just a couple of practice problems. You should do them before you do your quiz, right? But I'll make it due after the quiz, just so you have time to finesse it if you want to. Okay, and then so and then next week we're gonna start, and finish what we need in chapter 8 and maybe touch on 9.1, which is a kind of a simple extension. So kind of full steam ahead here. I know I've mentioned it before, but there are these extra practice problems. Now, these are just practice problems that I had typed up and I have kind of laying around. And so I just wanted to share them with you. There might be typos in, in some spots because I've kind of put them to the side. But if you want definitely for more practice on these means questions, then the mean inference, so it used to be chapter 5, then these are going to be really good for practice. And then I've posted the solutions as well, right? And so if you feel like you need more practice, maybe even just reading questions and trying to figure out what type of question it is. In fact, let me just go back and see here in the solutions, I even mentioned what type it is, right? And so then you can check to see, okay, did I get the right type of question? Because once you've decided what type of question you have, then you're smooth sailing, right? Then you can kind of go ahead and you can focus on that area of your formula sheet or whatever kind of summary thing you have going on at home, right? Maybe you have a piece of paper with all the rules for each of the types, and then you can just focus on that type, right? Because the type of question is not going to change, okay? So what are we doing today? We'll do a quick review, right? So from Friday, we talked, or the video I posted, we talked about paired data, right? I'll often call it a matched pairs type of question, right? For the question type, I'll call it matched pairs usually. And what we have is we technically have 2 samples, but those 2 samples are naturally paired, right? So if you're making 2 observations on the same subject, then you have paired data, right? So if I wrote a test today, and then a month from now, I write the test after studying, presumably, then my hypothesis might be that the difference in the scores is greater than 0, or depending on how I subtracted, right, maybe less than 0 if I've improved, that kind of thing. So there's a couple of little things to keep in mind for paired data. But what do? Even though I have 2 samples, right? So imagine your spreadsheet, you have a column and a column. So each column is going to be a sample, right? And those columns are naturally paired, okay? Then you have this paired data situation, right? So we have 2 samples, but they are naturally paired. They are naturally paired. Okay. So really what we mean is 2 observations on the same subject. We can even stretch it a little bit and say things like, okay, I'm going to assume that this plot of land, for example, behaves the same way that this other plot of land does, right? And so then I can consider them paired and I can measure those pairs. Even twins, right? Or even maybe even siblings, you could, depending on what you're measuring, right? You could consider them paired. So there's kind of, it doesn't have to be 2 observations on the same subject. It can be 2 observations on similar subjects. So you're assuming that they are paired, right? And so what did we say? Well, if we're going to analyze paired data, right? You've got these two samples, okay? Then what do? We calculate another column of the differences. And as long as you calculate those differences consistently, it doesn't matter which order you give it, right? But if one is larger than the other, then you're going to get a negative number one way and a positive number the other way. So those are things that you have to stay on top of, right? Oh, so we talked about, right? Our mean is now the mean of the differences, right? But then if we're interested in, okay, is there a difference here? A difference of 0 says, no, there's no difference here, right? So then our null hypothesis is always that the mean difference is 0, right? There's no difference between these two samples, right? And then our alternative is that the mean diff is not equal to 0, or if it's less than or greater than. And I think we saw an example where we wanted to show if one was less than the other, then we have to think about, okay, am I going to have a negative or a positive, right? But after that, our calculations are the exact same as they were in a one sample mean situation, because now you have one sample of differences, right? So, and notice I just put these little subscript diffs. You don't have to. Sometimes I'll use a D instead of the full diff, but it's just to highlight that we're testing for the differences. So here we're testing the mean difference, right? So paired data tests the mean difference. Okay. Today, I think it's 7.3, is the difference in means. In fact, let me just make sure, difference of two means. Right, so really, what does that look like? Well, that means I have something like mu1 minus mu2. That's the difference in two means, right? Mu1 and mu2. Okay, so paired data tests, sorry, I had a little something on my iPad. Paired data tests the mean difference, right? The mean of those differences. Whereas now we're talking about the difference of two means. And I tend to call these, to emphasize, independent means, okay? And so two independent sample means. So now thinking about your spreadsheet, right? So how have you collected your data? I find that helps, right? Because we can visualize that. So now again, I have two samples, but there's no way that I can match one group to another. And that's fine. That's probably the most common thing that we're going to have to deal with, actually. So, and so we've kind of built up to this point, and this is one of the most common things that we do. It's, we call it a two-sample t-test, okay? Because so far, right, all we've been doing, as soon as we're talking about a mean, right, whether it's one sample mean or the mean difference, or now we're going to find the difference of two means, they all calculate some version of t, right? And so we're going to see that again. So sometimes we'll call this a two-sample t-test. Okay. Good. Okay. Where it gets a little bit dicey is, okay, so I have two samples and there's no way I can kind of consolidate them into a difference column. And I'm even allowing for things like different sample sizes. Okay, so I might have two columns that aren't even the same length, but I can still compare those means, right? And so what we have though is we have a mean for, so a sample mean for group 1, we have a sample standard deviation and a sample size for group 1, and same thing for group 2. We've seen that before with two sample proportions, right? Where we had, okay, we have all this information, one from group 1 and from group 2, and then we have to kind of keep track of those. Same thing for means, but now we have kind of, I think, more information, right? We have a mean and a standard deviation and a sample size for each of these. And so we need to keep track of that, and we need to take them into account in our formulas. Okay, and so I posted those. Got so loud here. Sorry, I might close that. But first, okay. I did post these. I renamed it chapter 7. Oh yeah. Here's just a funny that I had. Someone sent this to me one term when I was obviously teaching this course. So my 4-year-old asked what happened when you drive over a stick of butter. Fair enough. And they said, it'll flatten. And he asked how I knew. And that's how we got here. So they're driving over that stick of butter. If you have a hypothesis, you got to test it, right? And so, and then also his wife was away. So it's kind of funny. Anyways, so, anyways, I got distracted. So let's see here. I wanted to go to here. So I'm going to steal this whole blurb, and remember, you've got it posted on Moodle, so I'm not mistaken. Well, let me just check. Pretty sure. Yeah. It's this chapter 7 notes, and then it says used to be chapter 5. That's why it's labeled chapter 5. And so I'm just going to steal from those. Okay. So when we have these two independent sample means, right, then we analyze the difference in these means. Okay. For example, if I have you know, the average sales for some group, right? So maybe, I don't know, I can't think of anything. Cough drop A and cough drop B, right? I have the sales. Which one am I going to take on? I want the one with the highest sales, right? So then what I do is I analyze those differences in the means, and then I choose the one that has the highest sales, if it's significant, right? And so the example that we're going to look at is for diamonds, kind of fun. And we're going to analyze the difference in mean price. Okay. So it's pretty common. Okay. So what you want to argue is that your two groups are independent of each other, right? So there's no natural pairing anymore in the observations, right? And that's common, right? Cough drop A, cough drop B. There's no reason to think that this cough drop gets linked with this cough drop, right? And that doesn't have to be. Okay. So you're going to have two columns of data, right, in your data set. And then you're going to have a mean, the standard deviation. And then, like I said, a cool thing is that they don't even have to have the same sample size. So you're going to have two different sample sizes from each group. Now, here is where I want to highlight this, because it's a really important distinction that we need to make. So matched pairs, we're analyzing the mean difference. Okay, so the mean of the differences, if you find that that helps, right? Because we found the differences and then we find the mean and the standard deviation of those differences. Whereas here, now we're talking about two sample means, then we're analyzing the difference in the means, okay? Which means you have mean one and mean two, and you take the difference of those two. Okay, so really important that you stay on top of that wording, okay, because they mean completely different things. All right, good. So let's see here, where was it? So what I want to do is, I guess this says it all. But what I want to do, so you have this and it kind of does a run through, but what I want to do is I want to go straight to the formula sheet and kind of dissect it from here. Okay, so we're going to do the same thing that's typed up in those notes, but I want to develop it together. Okay, so I'm not just giving it to you, or pouncing it on you rather. Okay. So two sample means questions, or you're going to analyze a difference of two means. Oh, kind of lagging there. Okay. So our hypothesis test is going to be a mu minus mu two. Now it doesn't matter which one is group one and which one is group two, as long as you're consistent. Okay, and in fact, you don't really need to be consistent, but you should be, right? And so here, right? It doesn't matter which group is one or two, as long as we're consistent. And like I said, it actually doesn't really matter, but you should be, right? As long as you keep your ones together and twos together. So as long as we are consistent. So with time and with practice, right, you might be more strategic about which one you're going to let be group one and which one you're going to let be group two, right? If you want a positive T, right, because we know that our table only gives us positive T's, and for some reason you want to avoid negatives, there's no reason to, but you can, right? How can you do that? You can let group one be the larger group, and group two have the smaller mean, and then you're going to have a positive number, right? So this is the parameter that we're interested in, mu1 minus mu2. So what's our point estimate, right? Our point estimate is going to be x1 bar minus x2 bar. Seems reasonable enough, right? And then technically what's going on down here in our T, right? Because our test statistic takes the deviation, right? So how far is my point estimate from my parameter? But what we're going to find is that in two sample means questions, our null hypothesis is that these two means are the same, right? Mu1 is equal to mu2. And then if I find enough evidence against that, then I can say, no, they're different from each other, or maybe less, mu1 is less than mu2, or mu1 is greater than mu2. It depends on the question, right? And so here, technically, you have minus mu1 minus mu2, right? But we always assume the null hypothesis is true. So if mu1 is equal to mu2, then mu1 minus mu2 must be 0, right? So that's another way that you could write this hypothesis, is mu1 minus mu2 is equal to 0. And that makes kind of more sense for talking about mu1 minus mu2, but I find that this is a little bit cleaner, right? And so here, equals 0 if mu1 is equal to mu2, right? So that's another one of those scenarios where it's always going to be -0, so we don't even write it down anymore, right? We've seen that 2 times already, right? We've seen it in proportions, so 2 sample proportions, and then we've seen it with paired data. Okay, so my T is a little bit more elaborate, right? Because I have information from 2 different samples, right? So I need to keep track of those, right? I've got the 2 sample means, I've got the standard deviations, and I want to highlight, right, that this is the standard error. And these 2 are the same. That's nice, right? Because that's not the case for proportions, where proportions had kind of a bigger standard error and it changed. So these are the same. So this is the standard error of x1 bar minus x2 bar, right? And I want to notice that these squares are on the standard deviation, right? So you've got the standard deviation of group 1 squared, and then divide by n1, put that to the side, so store it in your calculator somewhere, and then take S2, so the standard deviation of group 2, square it, then divide by n2, and then add it to that previous number, and then square root, right? So kind of a longer process. In general, we have the same ideas we've always had. Our test statistic finds how far is our sample point estimate from our hypothesized value, right? Taking into account the spread, and the spread in this case is this huge square root, right? It's not huge once you kind of get to know it, right? Once you have a t, you know what to do with a t, right? You can find your p-value by finding your degrees of freedom, right? And we'll talk about how to find that here, but you take the minimum of n1 minus 1 and n2 minus 1, really just the smallest sample size minus 1. Right? Once you have your degrees of freedom, you can go to the t-table and you can find a range for your p-values. Okay? Same thing with t star, right? So we know all these components already, we just haven't seen them used in this way yet, right? So that's kind of nice. So here, this really just says, take the smallest sample size minus 1. What you'll find eventually is this is a quicker way to write that than with words, right? If you take the minimum of n1 minus 1 and n2 minus 1, right, the result is the smallest sample size minus 1. Okay. I do want to say that technically, and if we go to those notes that I posted, technically, delete that, the degrees of freedom is this. I don't want to do that, okay? So, but, and you don't have to. So what we do is we take this more conservative approach, and this is the calculation that R would do, or if you're using Excel, it would use these degrees of freedom because it can, right? But we're not going to, that's crazy. So here I wanna, oh, and I'll, right, so technically, right. Technically we use this, right? But I'm happy just using the smallest sample size minus 1. And they're going to be approximately the same. What's going to happen is this degrees of freedom is going to be slightly smaller. Why? Because if we're being more conservative, then our degrees of freedom is going to be smaller, right? Because the larger our degrees of freedom are, the more sure of our estimate we are, right? So it's going to be smaller than the proper one. Yeah? All right, good. So kind of a fun place to be, right, is, okay, we know how to do hypothesis testing. We know how to do a confidence interval. And so now what I need to do basically for anything now is I need to tell you what the hypotheses are, right? Specifically the null hypothesis. What's the null hypothesis? And then from there, you can work out the alternative appropriate to whatever the question is. And you need the test statistic, T in this case, right? And then I tell you what the confidence interval is, and if you need it, I give you the degrees of freedom, and then you can kind of go from there. Okay, so like I said, I want to do a diamond example, which is in that, oh, there's notes I posted. All right. So I don't have one without the solutions, but I like this one. So we're going to work through it together. But if you need to, the solutions are in here, and I kind of talk around it in the notes. But so what I want to do is I want to use this example, and we are going to test the hypothesis, of course, but also build a confidence interval. Even though it doesn't ask for a confidence interval, I'll just show you how to do it. And then you'll have it. Okay. How can I? Make it, whoa, okay. So weights of diamonds are measured in carats. The difference between the size of a 0.99 carat diamond and a 1 carat diamond is undetectable to the naked human eye, right? So when we look at these things, we can't tell the difference. Okay, so that's important for this question. But does the price of a 1 carat diamond tend to be higher than the price of a 0.99 carat diamond? And this should say carat. We're going to test to see if there's a difference between the average price of 0.99 and 1 carat diamonds. Okay, so one thing I want you to pay attention to is, okay, now I'm remembering, and I feel like I have this eureka moment every term that I use this. I like this question, but there's a problem, because here I want to know if there's a difference, which would mean what? The alternative would be that mu1 is not equal to mu2, right? Whereas here, is there evidence that the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds? So we're going to focus on this one. Let's do the one-sided test, because that's what we're more interested in, right? Not just if there's a difference. We want to know if it's significantly higher, right? And so here, just to highlight what this would mean that the alternative is that mu1 is not equal to mu2, but we will do, or we will use the question below, right? So here, if it's higher, right? So let's focus on that. So sometimes we need to manipulate our data a little bit, okay? And so here it gets a little bit weird, okay? But it's really just so we're not dealing with tiny, tiny values, right? And so what we do is we're going to compare equivalent units, of course. So we're going to divide the prices of the 0.99 carat diamonds by 99 and 1 carat diamonds by 100. okay? And then we're gonna have point prices, okay? And so, so what we're actually going to compare is the price per point, right? So a 99 carat diamond would have 99 points, and 1 carat diamond would have 100 points, okay? Because then we can talk about those point prices. Otherwise, we're not comparing the same units, and that's a problem, right? So sometimes you'll need to manipulate these things, but for our questions, it would be outlined as it is here, right? Okay, here's something that we need to do. And in the end, you're gonna have some sort of summary like this. Either I give you the table, or it'll be kind of distributed in the text and you'll have to pull out all this information, okay? You collect 2 random samples of diamonds, okay? So here, right, I have 2 random samples. So I know I have a 2 sample test, right? And we're talking about the price, which is numerical, right? So we're talking about the mean. And then because I'm talking about 1 carat and 0.99 carat diamonds, right, there's no natural pairing there, right? And so then I have these 2 independent sample means question. Okay. This tells me the type is 2 independent sample means. Okay. So here, if I let my 1 carat diamond be group 1 and my 0.9 carat diamonds be group 2, what's another way that I could write this information? So I'm given X bar for each of the groups. I could subscript that, right? X1 bar, X2 bar, S1, S2, N1, N2. Okay, so what I'm going to do is I'm going to jot that down in here, X1 bar, X2 bar, just to highlight S1, S1, S2, N1, N2. So a lot of the time, 2 independent sample means questions is the easiest to pick out, right? For when you're finding your question type, because a lot of the time the information is summarized in a table like this, or the blurb has to say, okay, you collect a sample of 1 carat diamonds and you found the mean point price to be 53.43 with a standard deviation of 12.22 and a sample size of 30, right? And then you collected a 0.99, a sample of 23.99 carat diamonds and you found the mean price to be 44.50 with a standard deviation of 13.32. So it could be in the text like that. Often it's in a table, right? But even if it's in the text, you can put it in a table like this, right? So here, is there evidence that the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds? All right, here we go. So is there evidence? That means that we're going to do a hypothesis test, right? And then we're also going to follow up with a confidence interval, but I'll leave that until we're done with the hypothesis test. Step 1 is to state our hypotheses. Step 0 is checking the conditions. However, we were told that it was a random sample, right? And I usually don't test you guys on checking the conditions for means questions because it's so kind of breezy. It has to be a random sample and our sample sizes have to be large enough, or we have to assume that we're pulling from a normal distribution, which these sample sizes are large enough to assume normality. So we go ahead, right? Like I said, that's not something I get you to do, so I'm not writing it down, but it is something we should be doing, but can only do so much. We're only human. Okay, so in stating my hypotheses, my null hypothesis, because I have these two sample means, two independent sample means that I'm testing, my null hypothesis is that mu1 is equal to mu2. Okay. Usually, I would say you should use a question-specific subscript, okay? And so what we could use is we could use 199 if we wanted to, right? So here, instead of mu1 and mu2, I might have mu199, right? And I'll say use question-specific subscripts, at least in your hypotheses. When you're writing out your formula, it can be a little bit boggy, so you don't have to, and I usually forget to, right? But for your hypotheses, you should be really clear about what you're saying. So use question-specific subscripts in your hypotheses. Okay. My alternative hypothesis is going to be comparing mu100 to mu99, and I want to know if the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds. So then I need to have mu100 larger than mu99. This is where I make a little note to myself that this is a one-sided test. Why? Because I'm only concerned with mu100 being significantly larger than mu99, right? I don't care if it goes the other way, right? And so what we're saying is 5343 is larger than 4450, but taking into account the spread, right? Is it significantly larger? Okay, so that's what we're testing. So next step, step 2, is to do the test, which means calculate the test statistic. Step 2, do the test, which I'll clarify here, really means calculate the test statistic. But that's kind of boring. So I call it do the test, do the do. Okay. What's our T? You might not have it memorized yet, and that's okay. But our T is x1 bar minus x2 bar. And what I'll do here is I'm going to say technically, but we're going to ignore it, minus mu1 minus mu2, right? So technically we have this point estimate minus the hypothesized value, right? How far is my point estimate from my hypothesized value? But this hypothesized value is 0, right? So it goes away. And so usually we don't even write it out. I just wanted to write it out one more time. Over the square root of s1 squared over n1 plus s2 squared over n2. Oops. Notice that the square is only on the standard deviation, right? So you want to be really careful and you want to do that first. All right. So I'm going to grab this information here, copy, so that I can, okay, paste image there, so that I can plug it in here. I always say plug and chug, but that'd be a really fun theme for a math party, right? So I used to have math parties, a lot of them, and they were really fun. So now you can too, stats parties, 5343 minus 4450 technically minus 0. You don't have to write it, but I will for this one. Divided by the square root of 1222 squared over 30 plus 1332 squared over 23. Okay. Here we go. So T then, and usually what I do is I like to show the empty formula so that I show what I'm going to put stuff into, and then I show the numbers plugged in. Then you can skip straight down to the final answer if you want to. I know a lot of people are, how much work do I have to show? And we're just working online, so it's a little bit different. But if we were in person, right, you'd be handing stuff, written stuff in, and then, so how much do you have to show? And so here you could, in theory, skip to the bottom here. But what I'm gonna do is I'm gonna do this subtraction here. So, and I'm just gonna do it on my calculator. 5343 minus 4450 is 893. Divided by, and I'm going to do 1222 squared divided by 30. And that puts me at 4.9776133 repeating. Okay. I'm going to store that in my calculator. Again, if you don't know how to store things in calculator, and the other calculator that I have, but I don't know where it went. A lot of calculators will have a store button. And for these calculations especially, it's going to be really useful because then you can store it and then you can bring it back and you'll have all your decimal places, which is what we should have, right? So, I'm going to store that and move on to my next calculation, which is going to start with 1332, square it, then divide by 23, and then I can add this value. 1332 squared divided by 23 puts me at, so plus 7.714017391. And I'm sure it keeps going, but that's all I can see on my calculator. So then if I add that to recall that previous one, I get 12 something, right? 4.9 plus 7.7. Okay, and then you don't want to forget about the square root. Usually when people get values that are too, I feel like it's too small or too large, what happens? This is going to get smaller. They've forgotten to take the square root. That's like the most common thing. I don't know, this doesn't seem right. Did you take the square root? Right, so let's take that square root before, so square root of that, and then I'll jot that down. That 8.93 divided by 3.562531, oops, 505. Don't forget to take the square root. Okay, and then I can do 8.93 divided by that guy. And finally, I have a T that's equal to 2.50664499, and that's all I see on my screen, so that's good enough. T's, we round T's to 3 decimal places, right? At least 3 decimal places. There's no reason we have to round, but if you want to round, we round to at least 3 decimal places because that matches our table, right? So we're going to use the T table with our T. So T is roughly 2.507, right, to 3 decimal places. Nice. Okay. Woo, that's a big calculation, right? What's one benefit? Once we've done this calculation here, and I know that this whole square root, this is the standard error of x1 bar minus x2 bar, I can use that again when I do my confidence interval, right? Because it's going to be the same. And that's different from the proportions where we couldn't recycle, right? But now we can recycle this and we can use that calculation again. So as long as you've done it once, you can use it for both, right? Or either. And I should have saved it. I talked about storing my values in my calculator and then I did not do it. How can I get back there? 2.5. So I've still got this number on my screen. Let me try to finagle something here. What if I do 8.93 divided by, oops. Whew, I got back. So if you have this 2.50666, you can take 8.93 divided by that, and then you can get back to here, and then I'm going to store that. I'm going to store it so I can have it later. That's just me being lazy, ultimately. Yeah. All right. Step 3. All these steps, right? Notice how we are hopefully feeling a little more comfortable working through all these steps. It probably still feels like a lot, right? And it is. But this is why you have to take this course, is so that you can develop this, these steps and really stick with it, because then you can apply it to any type of question, right? Not just the ones that I introduce here in class, but you can apply it to other hypothesis testing questions. And there are many. All right. Step 3 is find the p-value. To use the t-table, which I'm assuming that you're doing, you could do this in R or Excel if you wanted to, but we're going to use the t-table. We need the degrees of freedom, right? And so I start off with the same standard blurb that I have been using for using the t-table. So I tell the reader, or my marker, more like it, exactly what I'm doing. Right. And so that's your job as well. I can only give you marks for things that you told me that you did. Right. And so it's better to just play it safe and just, here's everything I did. My profs in university would always make a big deal, because my handing out assignments and stuff, or handing them back, they'd be like, oh, this is Emily's assignment. So many pages, because I would always just write out exactly what I was doing. But they liked it, I think. So using the t-table with degrees of freedom. So this is the first time that we're going to do this. And we know it's the smallest sample size -1. Now, we can do that, right? You can write that out, but you'd have to write it out. I'm going to show you how to write it with the shorthand. So the degrees of freedom is the minimum of n1 minus 1 and n2 minus 1, which is going to be the minimum of, I think it was 30 and 23. Yeah. 30 minus 1 and 23 minus 1. And you can skip that step, but I just want to highlight what I'm doing, which is the minimum of 29 or 22, which is what? 22. Lucky for us, there is a 22 degrees of freedom row in our table, right? So then we can say, so this is the degrees of freedom that we're using, right? Because there is a 22 row. So using the t-table with degrees of freedom equal to 22, after all that work, right, we find And remember what I do for setting this up. It looks complicated, but we follow the same steps always for t, right? And so the absolute value of t equal to 2.507 is going to be between two values. And I can even set up the structure and then go back and fill in the blanks here. So our one-sided p-value, right? Remember, we want to know if, and that was way back here, if mu 100 is greater than mu 99. So that's a one-sided test, which I bring down to step 3. So we kind of sit on that for a little bit here. So now I want a one-sided p-value. So my one-sided p-value is going to be between two numbers. And then I can go and I can use the table. So let me see if I can kind of screenshot something. What's good here? Try to do a little bit more there. Kind of a big chunk here, but that's okay. All right. So we have 22 degrees of freedom. So, and I know that's a row on my table. So that's where I have to stay now. So what do? I find where would 2.507 go? Then I would go and I keep moving out 2.508. Ooh, so close, right? If this was 2.507, what would you do? You would have to go and maybe not round so much, right? So we rounded to 2.507. So you're not stuck, right? You just can't round as much if it ends up being one of the values. Now we know that it's somewhere between these two here. Right? So what do? I jot those down here. That's how I show my work, right? So I went to the t table. I found my degrees of freedom. We already talked about that. And then t is between 2.183 and 2.508. So my one-sided p-value, let's highlight those here, I think. And is going to be between these two values, but I have to read them from right to left, right? Because I have to list the smallest value first and then my bigger value. So my one-sided p-value is between 0.01 and 0.02. So then I can write that here, 0.01 and 0.02. Even though it's just a range, right? We're comfortable with using, or maybe not comfortable, but we're used to using the ranges now, and we can still gather the same information, right? Is that less than our alpha level? There was no alpha level given, that's okay. We'll assume 0.05, okay? So we have our p-value. Now we're ready for the moneymaker, right? Our conclusion. So here, step 4 is our conclusion. First, we compare our p-value to our alpha level, right? We're going to assume 0.05, so I'm going to say that. Then, if the p is low, then the null hypothesis must go, or something like that, right? So then, if the p-value is less than the alpha level, same conclusion as always, then we have enough evidence to reject H0 in favor of HA, right? Did you ever think in a million years when we first started talking about confidence intervals and hypothesis testing that you would do so many of these? It's crazy, right? And then of course their conclusion in terms of the question. So since and notice how I always use the same conclusion kind of structure here. So since our one-sided p-value right? I highlight that I had a one-sided p-value, also kind of showing off that everything that I know, right? So since our one-sided p-value is between 0.01 and 0.02, 0.01 and 0.02, it is less than our assumed alpha level. It's less than our assumed alpha level of 0.05, right? Both 0.01 and 0.02 are less than 0.05, so it's somewhere in there. That's fine, it's less than 0.05. Okay, less than our assumed alpha level of 0.05, which means we have enough evidence to reject H0. We have enough evidence to reject H0 in favor of HA, right? If you're rejecting it, you should probably say in favor of what? In favor of HA. And then finally, right, what's our conclusion in terms of the question? So that's when I go back to the actual question and I reword the question as an answer. So I'm going to copy this. I'm going to delete it after because it's a little messy, but I'm going to steal the wording, right? Therefore, there is evidence that the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds, right? So therefore, there is evidence that the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds. It's a lot of writing, but it's all kind of mundane, right? We're just rewriting the question as an answer. So now I can delete that. Oh, delete. Yeah. Okay. What can we do with that? What would that mean? So there's a couple of different things, and it's not really our job to determine what's what to do with this finding, right? But for me, I'm cheap, so if they look the same, and I know that that the 1 carat diamonds are significantly more expensive, I would probably go for the 0.99 carat diamond, right? They look the same, right? But it just kind of depends on the scenario. So good. I just want to go through and I want to highlight, right, the 3 parts of our conclusion like we were doing in the past, right? So we compare our p-value to our alpha level. That's, standard now. And then our conclusion in terms of the null hypothesis, right? And so we either have enough evidence to reject H0 or we do not have enough evidence to reject H0. And that's because we did all our testing assuming the null hypothesis was true, right? So, and then finally, our moneymaker, and I like to put a little cup there so it kind of closes off, is the conclusion in terms of the question, right? You just reword the question as an answer. Nice. So The hypothesis test tells us whether there is a significant difference or if one is significantly higher than the other, right? But it doesn't tell us how much higher. And that's where the confidence interval comes in, right? So a hypothesis test here, it tells us if there is, or sorry, I'll go specific to this question, right? So it tells us the 1 carat diamonds cost significantly more than 0.99 carat diamonds, right? And we're talking on average, right? We're analyzing the averages. Whereas a confidence interval tells us how much more expensive, right? So it tells us the actual difference in the costs. So a confidence interval tells us how much more 1 carat diamonds costs, and I just wrote C because I got lazy, tells us how much more 1 carat diamonds costs than 0.99 carat diamonds. So if we were to build a 95% confidence interval, just kind of sticking to the usual here. So a follow-up question would be construct a 95% confidence interval for the mean difference in, or sorry, I made it a paired samples. That doesn't make sense. No, it's the difference in mean for the difference in mean costs of the diamonds. Told you it was important to keep track of the mean difference or the difference in means. Okay, so, and I made it kind of a shorter blurb because I didn't want to have to write out too much. Right? So what can we do? We have, so our confidence interval, as always, it's our point estimate plus minus our critical value, which is a T star in this case, right? And we already know our degrees of freedom is 22, so you can use that, right? You don't have to show it again. And then the standard error of the point estimate, which we have already calculated and I saved in my calculator. All right, so it's going to be x1 bar minus x2 bar, right? That's my point estimate, plus minus T star, and then times the square root of S1 squared over N1 plus S2 squared over N2. Now, what I'm going to do is, and you're allowed to do this, because I've already shown this calculation, I've already done this calculation, okay? I'm going to do this. This is equal to, I think it was like 3. This is equal to this. I'll make it pink there. From previous part. Okay, so you're allowed to save yourself that headache. And also we know that this is 8.93. I think it was, yeah, 8.93. From previous part. So the only thing that we don't know here is this T star. T star, that's not a very nice T. T star, and then what I'm going to do is I'm going to put the little degrees of freedom here, 22 degrees of freedom. And what I can do is go to the table, right? And I'm gonna grab, I'm sure you guys are all comfortable with this now. Okay, let me see here. So I'm not gonna use too much space to do it. I need to show you guys where it came from though. Copy and delete and paste. Okay. I'm gonna zoom in here. So I've got, whoops. Oh my gosh. I need a smaller highlighter. I still have 22 degrees of freedom. And I want a 95% confidence interval. So then I have a T star of 2.074. T star is 2.074. Notice how it's always around 2, right? And that's going back to the 68, 95, 99.7 rule. So 2 is a good approximation, but we want to be specific because we can be. So then I have all the information that I need. It's just a matter of plugging these things in. So I have 8.93 plus minus 2.074 times 3.562531,505, which I have stored in my calculator, right? So I'm gonna grab that. .93, so I'm gonna do recall that guy, and then times 2.074, 7.388690,342. That's my margin of error, right? And then now what I have to do is I have to first subtract. So I'm gonna store this. I'm going to do 8.93 minus that. Puts me at 1.541309,658. And then if I add it, 8.93 plus that guy, whoops, shift, oh my gosh, shift, recall. Then I get to 16.31869034. Remember that we're talking about prices, it's specifically point prices, right? And so here, what we're talking about is the difference in point prices, right? So these are differences, and 1.54, if group 1 is the 1 carat diamonds and group 2 is the 99 carat diamonds, then a difference of 1.54 means that the group 1 costs 1.54 more per point than group 2. Okay, and so what's nice about money amounts is that we can just round to 2 decimal places, right? Because that's money has 2 decimal places. And so what we can find is that our confidence interval, it's on a new page, so I'll kind of rewrite it here, but is 154 up to 1632. Okay. So let's interpret our confidence interval first. all right? Keeping in mind that this is the difference in point prices. So notice that these are differences in point prices. Okay. Right, because we're talking about the mean, the difference in means, or is the difference in, and maybe what I'll say is in mean point prices, just to emphasize. So if we're going to interpret this, right, we use the same blurb that we always do. So we're 95% confident. We are 95% confident the interval from $1.54 to 1632 captures, oops, that doesn't look like captures. So we're 95% confident the interval from 154 to 1632 captures the true difference in mean point prices. Right? Usually I would refer back to the questions here. So construct a 95% confidence interval for, and then that's what I'm interpreting, right? The difference in mean costs of the diamonds, but I said point prices, that they mean the same thing, so it's okay. In mean point prices, and I'll elaborate here of 1 carat and 0.99 carat diamonds. Okay, so if we remember, right, so we took mu 100 minus mu 99, and this difference is somewhere between 1.54 and 16.32. We're 95% confident of that, right? And so what we're saying is that the 1 carat diamond on average costs between 154 more per point up to 1632 more per point than the 0.99 carat diamonds, right? So in terms of the differences, right? So we have found, or we are 95% confident that the 1 carat diamonds cost between $1.54 more up to 1632 more per point than 0.99 carat diamonds. In general, right, a 1 carat diamond has 100 points, right? So now we're talking about a difference of $154 or $1,632. So that's our range, but I wouldn't expect you to go that far. Okay, and so just remember that you're talking about the difference in the means as opposed to the mean of the differences. And I'm all out of time, but really nice and nice way to wrap up. If you have any questions, let me know. Otherwise, I will see you on Thursday. Stop this here.